Welcome to The Explainer. Today, we're embarking on a pretty fascinating journey that touches literally everything in our universe. Yes, that includes you and me. We're diving headfirst into the physics of energy, work, and power. Now, I know, physics can sometimes sound, well, incredibly abstract. But today, we're going to ground it completely in reality. We're going to trace a straight line from that breakfast on your plate this morning all the way to the rigid equations that govern heavy machinery. It's totally going to shift how you see the world around you. So let's get energized and jump right in.
So let's kick things off with a super fundamental and honestly incredibly relatable question. Why do we actually need to eat? I mean, it's a daily human experience, right? We've all heard our entire lives that breakfast is the most important meal of the day. But if we look at it from a purely mechanical standpoint, why is that biological drive just so incredibly strong?
We all know this exact feeling, don't we? You wake up, or, the 3 p.m. slump rolls around, and your body is literally just screaming, I need food. It's a primal urge. But I want you to think past those hunger pangs for just a second. What do we actually gain when we finally sit down and consume a meal? What is the physical currency we're extracting from our food?
Well, the truth is, whether you're inhaling a massive stack of burgers or just having a simple bowl of oatmeal, food provides the exact same thing to our bodies that a tank of gas provides to a car engine. We're taking in fuel. And what kind of fuel are we extracting? Energy. The end goal is always, absolutely the same. Food is energy.
So, to conquer these foundational concepts today, we've got a roadmap with 4 stops. Number 1, defining energy. Number 2, mechanical versus non-mechanical energy. Number 3, kinetic and potential energy. And finally, number 4, calculating work and power.
All right, stop number 1, defining energy.
Now, in the world of physics, energy is formally defined as the ability or capacity to do work. And I really want you to absorb that specific word, capacity. If you possess energy, it means you possess the potential to actually accomplish a task. It's basically the currency that allows things to happen in the physical world. Without it, everything literally just stands still. Which naturally leads us to the result of having all that energy. Think of a furiously typing cat just mashing a keyboard. It's a pretty funny way to think about physical activity and work as the direct, visible result of having energy. When you have the capacity to do work and you apply it, you get motion, you get actual results, you get a task completed, whether that task is typing out a frantic essay or, lifting a heavy box.
Moving right along to stop number 2, mechanical versus non-mechanical energy.
In physics, there's a really clear, definitive boundary here. On one side, we have mechanical energy, and this is the total amount of energy that depends entirely on an object's physical position or its motion. On the flip side, we have non-mechanical energy, which definitively does not depend on motion. It's a perfect contrast, really. You just have to ask yourself, is the object's physical place in space or its movement through space the source of the energy? If the answer is yes, it's mechanical. If no, it's non-mechanical.
Just to give you a concrete idea of what falls outside that mechanical realm, consider things like thermal energy, nuclear energy, heat, and chemical energy. These are all types of energy that operate totally independently of a large object's visible physical motion. Think about a standard battery, for instance. It holds chemical energy whether it's sitting completely still on your desk or rolling across the floor.
Which brings us to part 3, kinetic and potential energy.
So as we break down mechanical energy, you'll see it divides into a few major subcategories based directly on what we just talked about. First up is kinetic energy, which depends entirely on motion. Basically, if it's moving, it's got kinetic energy. Second is potential energy, which depends entirely on position. And sitting right under potential energy, we find specific types, like gravitational potential energy, which is all about how high up something is, and elastic potential energy, kind of like a stretched rubber band. When you add it all up, it's just the energy of motion plus the energy of position.
Let's look at a practical, if maybe slightly chaotic example. When someone is falling, say, out of the sky, they are very much in motion, meaning we are witnessing kinetic energy firsthand. But why are they falling in the first place? Well, it's because of their position high above the ground, meaning their gravitational potential energy was converted straight into that motion. It's gravity doing work in real time.
Think about a child pushing a toy car across the floor. That captures this entire sequence just perfectly. The kid has energy, probably from the snacks they ate earlier, right?
They're applying that energy to do work, putting the toy car into motion. So they are literally transferring their internal chemical energy right into the mechanical kinetic energy of that little car.
And that brings us to our final stop, number 4, calculating work and power.
All right, let's look at a real-world scenario. Imagine having to push a massive 150-kilogram crate up a 10-meter ramp. To calculate the actual work required to do that, physics uses a super simple relationship. Work equals force times distance. To pull this off, the worker has to apply enough physical force to overcome the crate's gravitational potential energy across a distance of 10 meters. As you can guess, that requires a massive capacity for energy.
Now let's shift gears from human work to machine power. Picture an elevator motor that does 60,000 joules of work in exactly 30 seconds. This introduces a really fascinating new layer to all of this: time. See, power isn't just about how much work you can do, it's about how fast you can do it. By dividing the total work by the time it took, we figure out that this specific motor has a power output of 2,000 joules per second, or as it's more commonly called, 2,000 watts.
Now we can easily flip the script on this. If you already know a motor has a power output of 200 joules per second and you run that motor for 15 seconds, well, you just multiply them together. It will accomplish 3,000 joules of total work in that time frame. It just goes to show how the elements of energy, work, and time are completely inextricably linked.
So, bringing our whole journey full circle today, I really want you to remember this one simple but honestly profound pathway. Whether we're talking about a worker pushing a huge 150-kilogram crate up a ramp, an industrial elevator motor lifting heavy steel, or just you eating breakfast in the morning, it all boils down to this exact sequence. Food or fuel is converted into energy, which then gives the capacity to perform work, resulting in physical activity. It is a universal constant.
But before we wrap up today, I want to leave you with a thought-provoking little question straight from our source material. I want you to really think about this, based on everything we've just uncovered. Does energy actually require movement to be considered energy?
As you chew on that, consider a perfectly still tent stake driven deep into the ground. It has absolute zero kinetic energy, right? It isn't moving an inch, but based on its position, based on the tight tension of the rope attached to it, how much invisible potential energy is hiding right there. I invite you to just take a look around your own room right now and wonder how much invisible energy is quietly hiding in the stationary objects completely surrounding you. Thank you so much for joining me on this explainer, and definitely keep questioning the physics of the world around you.
Since you reached this far, if you enjoy this video, hit that like button and share this to your friends. As Sir Cedric always says, learning is forever. See you next time. Bye.